Go. Okay, everybody can see that, right?
Yes.
Okay. Looking at this graph, what do you think this represents? Yep. TDs, touchdowns scored. So that would be the offense and the defense for the Broncos. Right? Who, based on this, what do you think the average, around the average that, well, yeah, what do you think the average is that the defense allows per game? How many touchdowns does the Denver defense allow the other team to score usually? What do you think? Take a look.
So each one represents a whole touchdown?
Right. So here would be, these bars would be the amount of games where the Denver defense allowed the other team to score at least no touchdowns, 1 touchdown, 2 touchdowns, 3 touchdowns, or 4. So this is basically going into points of 7. So anything below 7 would represent the games that they, so whoever they played here, and I think that was San Diego, which is not very good, basically they held him to 3 points. So the other team didn't even score a touchdown. What on average does the defense allow the other team to score? How many points do you think? Anybody? Defense.
The Denver defense allows
2 touchdowns. Yes, pretty dang close, JC. Good job. Thank you. Here's the deal is, what I want to show you, and then how much do you think the Broncos normally score? About 3 touchdowns, right? That's a sign of a good team, right? Their offense is scoring more points than they allow the defense to score. Therefore, they're going to the playoffs. Here's what I want you to see in this data, and I want you to kind of use this as a way to kind of visualize it, is that do the Broncos defense, do they allow the other team to score less than 2 touchdowns? No, right? Sometimes they allow them to score more, sometimes they allow them to score less. But you can see here, and what I'm going to try to show you, see that curve right here? This is a magical curve in statistics. This is distribution. This is basically showing you the area under this curve represents the Denver defense. On average, they typically allow a team to score less than 2 touchdowns, but sometimes they allow them to score less, sometimes they allow them to score more. But on average, the middle of this hill usually is what normally happens. Same way with the offense, right? That you can kind of draw a curve around this distribution. That when we present things like average score or median score, it's only 1 point on this hill. Okay? And if you actually look at the results, the Denver defense on average allows the other team to score 18.7 points, which is actually less than 3 touchdowns. It's around 2.
Do you remember when the Seahawks, when they were at their defense at their peak, what they were allowing on average?
No, but we can totally figure that out. Actually, it should be on your main page for that Excel file I just sent. Then we look at the offense. On average, they're scoring about 22.7. Median is 23.5. So based on this, I would say the Denver defense typically scores greater than their average based on this median value, which is a good sign. Here's what I want you to see is that when we talk about seasons and we talk about numbers, we talk about averages, that's just 1 point, one little line on this curve. But what we do in mathematics and what we do in statistics and what's going to be important for this class is we basically model, anytime you take any kind of measurement on anything, there's a variation to that. And we're going to talk about that. Who can think of something? So this is called standard distribution. Basically, you have kind of a middle point and then you have receding on both sides. What other kind of trait? Don't even think about sports. Think about us humans. What other trait do you think would follow this kind of curve? Weight, yeah. What else? Height. Anything else?
Speed.
Speed. Basically, here's the thing: is about anything you measure, two people are never going to get the same measurement for, right? And we do this in disease a lot. When I look at these biological data sets, all these people have cancer, right? But they don't have the same kind of cancer. Some might be worse, some might be better. There's variation in that cancer. And so what I'm trying to get you to see is that all these numbers we look at kind of have a iceberg underneath them. And we're going to talk about that. So let's talk about, we mentioned height, right? So this is a picture. These are all women that were in this particular class. They are grouped based on their height, right? Shortest to tallest. You can see this same kind of curve here, right? What do you think the average height of women is?
5'4".
5'4". G Money got it. Yeah, it's about 5'4". Does that mean all women are 5'4"?
No.
V, are you 5'4"? No. ST, are you 5'4"? No. Right. That there is variation, and we're going to talk about this curve. This curve is very, very important. Because when we compare teams, we got to take this curve into effect. That not all teams or no teams score the same amount of points every game. Ever. I don't think so. All right, well, let's take a look at this curve. And I'm going to show you what this curve means. We're going to give it all kinds of little terms that you're going to use throughout this course. So again, here's the curve, right? What does this point represent?
Peak.
As a peak, it is the average, yes. So this would be the average, right? So this is the middle point. This is what you use to ground your numbers, to ground this hill. This just tells you where your hill is, right? So you got the mean. Call it average 2. Now, when we start talking about the distance away, how wide this hill is, and that plays a huge role, right? That if I have a team that scores from 0 to like 70, that's going to be very hard to predict because that's a very, very wide hill, right? Compared to a team that scores maybe, anywhere from 7 to, say, 31. That's a smaller hill. That's easier to model. Who here has heard of standard deviation?
We talked about it last year.
Oh, I did?
Yeah.
Oh, I did, didn't I? Oh, I love me. Yes, I talked about standard deviation. So basically, standard deviation is one of those metrics that helps you determine how wide this hill is. If you go one standard deviation, and it's basically based on the mean minus all your values. If you go one standard deviation from either side of the mean, that's 68%. Okay? That represents 68% of your data. If this was the football teams we were looking at, this would represent the team 68% of the season. 68% of the Broncos scoring is going to be in this area here. Now here's the magic number. If we go 2 standard deviations away from the mean, now we're at 95%. This value is very, very important. That if something happened 95% of the time, what would you think? Most likely to happen, right? Statistics sees it the same way. If we go 2 standard deviations out, we represent 95% of the data. This is called the 95% confidence interval. This is like the sweet spot of the data. That if I'm measuring, say, weight, right, and I get all of these people, they all fall in here, but say then I start measuring another population and say they're like really, really low outside of this or really, really high, that's unusual. That gets my attention. That I expect everything, think of this as kind of a big bucket. You know, if everything's falling in the bucket, I'm okay. Once it falls outside the bucket, that means something's different. And that's what we look for. So outside of this 95% confidence interval, how much of the area is left? 5%. And I'm going to tell you that's going to be key. And I'll explain how that's going to be key later. So again, right. So anything outside of this basically represents 5%. These are called the tails. Has anybody heard of tails before besides on animals? Tails basically, this is the outside of the data. This is where statisticians love, right? We love this little yellow area here, the tails, because this is where all the cool stuff happens, right? The unusual stuff, the things we don't expect. People sometimes are born with tails. Actually, they all are born with tails. I don't know what that means, and I don't even want to know. Okay, so again, this is normal distribution here, though, right? You see that you have a central point, and you see the number of people that are associated with this. Say this is either score or weight or height, that the farther you go down or above this, the number of people with that particular trait drops off. Does everybody see that? Right? So if this was height, this would be, for women, this would be 5'4". This might be, you might have like 3 women at like 2 foot tall. I don't know, is there any women at 2 foot tall? Probably. And then you might have a woman here who's like, 7 foot tall.
I'm 7 foot tall.
Yeah, I don't think so. But you can see, and this is what makes life nice, is that when we looked at the scores, did it look like this bell curve? Kind of?
Yeah.
Yeah, totally did. Do you think that's the only way that these things can be distributed? What other ways?
Like,
How else would that curve look? And Balboa, since you opened your mouth, I want you to draw me a curve that doesn't look like that.
doesn't look like that?
Talking about distribution, what other types of distribution are there? And Balboa did a great drawing of one of those. You did.
Hey, thanks, man.
Here's what you can have, is bimodal distribution. Bimodal. No. If we look at look at this graph here. Here are the number of birds with a particular beak size. This beak size is increasing, right? That we have a bunch of birds, this kind of large group of birds with very, very small beaks, and then we have this other group with very much larger beaks. And there's really nothing in between here, right? There's no gradual increase. Why do you think that, based on this example, how do you think that might come about?
Natural selection.
Yeah, as far as,
Some birds eat small stuff, while seeds and produce.
that's awesome. Good job, JC.
I mean,
You came back. You might have had a so-so break, but you came back with knowledge. Yes, that actually this graph here is that there's 2 kinds of flowers on this island. That some of the birds have evolved to feed on one type of flower, while the other ones have evolved to feed on the other. What we notice is there's not really much in between here. And if we looked at the mean, right, where would the mean be? Be about right here, wouldn't it? Yeah. Which is a lot different than being in the middle of that hill. It can also be skewed. So if we look at height here, right? If we look at height, what would happen if we were measuring women's height and the people that were measuring height decided to hang out at a women's basketball camp?
Well, women would be taller.
Yes, they would. Right? that you would have a larger proportion of taller women there, so you would actually skew this to the women that are taller. Now what happens if we were actually measuring men's height at, say, a jockey's camp? You know what jockeys are, right? Yeah, the little guys that ride the horses, right? They would be actually, then we would skew this to the smaller individuals. These are all examples of not normal distribution, that we don't see that nice bell curve. Most statistics use the bell curves. And I'm going to tell you right now, probably most data that we're going to look at in this class are going to be normally distributed. But I wanted to show you the other types, just to let you know that those exist out there. All right. I have told you about the statistical test, right?
Yeah, but like how far it travels or something?
Yeah. You guys want to hear the story again?
Yeah.
Okay, good. Because I'm going to tell it to you. So remember, so here's the deal is, given the fact that if I want to compare, say, Denver versus the Raiders, I can't just compare numbers. I need to take these hills into account because these hills play a huge role. And what I'm going to tell you about is what we're going to do today is we're going to learn this test that will allow us to do that. That takes the hills into account to determine whether two hills are very much different from each other. And again, as I think I previously mentioned in my opening lecture, this test was developed based on beer, right? Everybody's heard of Guinness beer?
Yeah.
Maybe, sorta.
It's my favorite.
That's your favorite. I didn't hear that. La 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 la. Yeah. So basically what it was developed by this guy named William Gossett. Statistician. He looks very serious, doesn't he? Yes, he does. All of them do. When you actually look at all these like old like pictures of scientists, they're never ever smiling. I don't know why.
I think I know why, because like that was like the culture. People didn't really like to smile.
That's true.
Serious face.
Yeah. Yeah, probably. Well, this guy was pretty smart. Is that, remember, he was slumming, you know, he was working for the brewery, but he was the apprentice to like one of the guys that developed the Pearson correlation test. And we're going to talk about that later. It's a huge, huge test. It's an awesome test. Well, anyway, he was working for the brewery, and then, again, the brewery just wanted to know if shipping their beer farther than, say, 70 miles would cause the beer to taste worse than it did near the brewery. As you've seen with these football teams, we can measure a lot of stuff, right? You can do the same thing with beer. There's the reflective index, you know, how dark is it, how carbonated, all kinds of things you can measure. So he decided to do this. He was going to take all these measurements, and he realized that every time he measured a beer, even if he measured in the same place, it probably wouldn't be the same number. But again, it's going to be this hill around this kind of central number. So he basically did that. Did the hills, and what he did, and this is what makes his unusual, is he would see how far it actually overlapped. The more these two hills, based on his conditions, overlapped, the more different they were. Or the less. The less they overlapped, the more different they were. If they overlap past 5%, remember, that's that 95% confidence interval. If they overlap more than 5%, he would say they're probably not that different. And this has been a number forever. So when you hear p-value, scientists usually use a p-value of 5% to show that something's different, that it has to be under that. Let me do it. Well, I forgot to finish with this story. So when he published this, so I'm going to tell you right now, the Ttest is the most popular, most well-used statistical test on this planet. Since he was working for the brewery, he didn't want anybody to know that he was doing that. So when he published his paper, he basically wrote it as a student. He said student on it because he didn't want to put his name. Can you imagine that? The world's greatest statistical test, and he didn't want his name on it. So from this day forth, and you can look this stuff up, it's called the student's Ttest. just because he didn't want anybody to know he was working for the brewery.
Students Ttest.
It is. You can look it up.
How do we know it was him?
What's that?
I don't know what it is.
Because he had all his notes and everything. Everybody knew it was him. He just didn't want to. I mean, he was working with the brewery. The brewery knew.
Oh, yeah, so you.
Yeah, so later on, like, of course, everybody knew. And in fact, you know, after everybody started using it and it became popular, he was like, hey, that's mine, that's mine. But the student T-test always stuck. So it's always been called, it's not a Gossett T-test, it's not a Williams T-test, it's a student's T-test. Poor man. But now you know about him. So there. So how do we use this T-test he talks about? You know, the traditional way to kind of explain this test is to go, have you guys heard null hypothesis and alternative hypothesis? Kind of just here and there. I think that's a kind of a terrible way to learn this kind of stuff. So what I do is, you know, I consider the p-value the overlap. Let's go back to our human height example, right? The red line represents the human height in females for the population. The blue line represents the males. Who on average is taller?
Males.
Yeah, males. And you're probably going, well, I knew that. Well, now we have numbers. And again, this is a pretty accurate representation of the amount of women and men at a particular height in our population. Do you think we measured every person on this planet to get these curves?
No.
No, of course not. That's what we do, and that's what we're doing with these numbers. Is basically what we do is we measure a certain amount. If we have enough people, and it's usually at least 3, we can kind of draw these curves and estimate what that distribution looks like. Does everybody understand?
Yeah.
Cool. Okay, so based on this example, you said males are on average taller. Say I'm talking to a buddy on the telephone, and he says, hey, I'm with somebody who's this tall. What would be the height where it'd be an equal proportion? He didn't tell you a name or anything. He just says, I'm with this person at this particular height. What height do you think would be where it'd be an equal chance of him talking to a male or female? 5'7". Yes, JC, thank you.
True.
Does everybody see that?
Oh, wow.
Right, I mean,
It's that point where they curve, right? That at this point, the chance of being male or female at this particular height is the same. Okay? Now I'm going to ask you this question. Here's what I'm trying to get you to see is once we draw these curves, then we can ask all kinds of cool questions. Okay. Say I'm talking to somebody and he goes, hey, I'm having a great time. I'm hanging out with this person. He's 5'9". What is the chances, do you think, of that person talking to a male?
50%?
15%. Now look at the areas under the curve. That's what I'm trying to get you to look at. At this height, the area represents the amount of people at that particular height that are male or female.
Oh,
Male.
What do you think? If I'm talking to my buddy, he says, hey, I'm talking to somebody who's 5'9", what are the chances that person's a male?
It's 14.
Okay, actually, don't look at this side because we're just looking at one point.
2, so it's like 7 times more likely.
Pretty close, maybe.
what?
Here's what we do is we take basically the area under that point, right? That this green area probably represents 90% of this distance from this point here all the way to 0. About 10% of this line is made up of females. Does everybody see that? So next time somebody asks you, hey, I'm talking to somebody who's 5'9", you can go, hey, I bet you're talking to a male. Yeah, because that always comes up in conversation. Here's what I want you to see, though, is that the p-value, where do you think the p-value is? How do we determine the p-value?
You
Remember, it's where it crosses. So this area here is where it crosses. How much of this total areas of both curves do you think it represents? 30% maybe? 40%? 20 maybe? I think a little, maybe 30. I go 30. This matters because the more overlap there is, right? The bigger the p-value, the closer these two hills are closer together, which would tell you that they're more than likely not very different. Does that make sense? Here's what happens in biology. I'll analyze a gene, and in the disease, this gene might be going nuts, just expressing lots and lots of product. In, say, normal person, it's really not on very much. So if I did these curves, this overlap would be incredibly small. This triangle would be tiny, 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 like 0.0001%. When that happens in science, we go, yay, it's lower. But, when these are closer together, what would happen if the p-value equaled the entire area under the curve? It's the same. Good job, JC. Yes. If this p-value is the same, basically the value of your curve, then these two things are closer together. They overlap. They overlap completely. In that case, I would say you're probably not looking at something that's different. Here's what I want you to see is that we use this stuff to see what's truly different in science. So based on this graph, do you think height's a good way to determine who's male or female? Maybe not. At the higher heights, maybe, right? But here's the problem. Even at the lower heights, there's not a 100% guarantee, right? That the smallest human is probably just as small as the smallest female. And the largest male is pretty close to being as tall as the largest female. The very, very largest. The outliers is what I'm talking about. On average, you are absolutely right. There is a difference. But I would say if I was going to use, I wouldn't use human height to determine what's different. So you can see what we, like I mentioned, we use this p-value to determine what's different. Not only determine what's different, but how different it truly is. That the lower the p-value, the more different these two things that we're looking at are. And there's all kinds of tests to generate these p-values. And again, I mentioned the Ttest, but there's analysis of variance. There's also this Mann-Whitney test that we'll talk about later. But again, what you can do is you look at all the genes and say a bunch of healthy people and people with a disease, do this test, and it'll give you a list of genes that are different. When we get into bioinformatics, this is a gene list we're going after, right? If I'm looking at a disease, I want to know what genes are different. Now that I know what's different, now I can concentrate on these and look for maybe a cure. Does everybody see that? All right. Congratulations, you now know what a p-value is and a t-test. And you probably are in maybe the 2% of the population that does know that. Not a lot of people know that, which is a shame.